So, welcome to EGR340. Then, first we will work out the problems on pure substances. Then, I want to work out the problems on chapter 4. So, you should have been seen this handout which I posted on chapter 4. And then I would discuss chapter 5 and slides for chapter 5 I've already emailed. Everyone clear about the agenda, what we need? Once again, you need chapter 3 notes, steam tables, SI. These steam tables are slightly different. And then chapter 4 notes. So first half of the lesson, we are going to work out the problems. Then I would discuss the next chapter, which is first law applied to steady flow process. And at the end, you are going to have an in-class quiz. And that's going to be open notes quiz. And you can, if you have had troubles printing your notes or the handouts, you are welcome. You can use your computer or phone, but please follow the honor code. So please follow the honor code, but you are welcome to use the notes if you don't have a hard copy. Now, okay. So properties of pure substances. And when I say pure substance, I mean water. Now, the most important diagram that we have studied again and again and again is something like this. You have either T or P on y-axis. This is the temperature. And then you have specific volume on x-axis. Now, the way this works is initially the pressure increases inside the liquid and gas region. You have liquid on the left hand side. You have liquid plus gas mixture under the dome, and then you have gas on the other side. Steam could be anywhere in between this region. This is called as saturated liquid line. Saturated liquid line. And this is called as saturated vapor line. So on the left hand side, you have saturated liquid. On the right hand side, you have saturated vapor. Now what we are going to do is, we are going to solve the problem. But when we solve the problem, what we need to do is we need to find out the appropriate properties using the steam table. And in the past class, 2 classes ago, I thought I worked out for the first 2 problems from the notes. Now I will work out the next problem, which is problem 3.3. Problem 3.3. Calculate volume, density, enthalpy, and entropy of 2 kilogram of water at 80 degrees C and 2 bar. Now, first and foremost question that we need to ask is, what is the state of this water? So pressure P is equal to 2 bar, temperature T is equal to 80 degrees C. Now I want you to quickly go through the chart, the steam table, and I want you to track the temperature and pressure. So if you look at, if you look at the very first table, you can see the temperature of 80 degrees. Can you see the very first table, table A4? Table A4. In table A4, can you see temperature is 80 degrees, Psat is 47.41, 41 kilopascal. Then what you have is, you have all other properties. Are you able to track this? Can you see? Which is line number, row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17th row. Now we will collect appropriate properties. So VF is 0.00102. Now, first of all, my question to you is, tell me, what is the state of the water? So state of the water, I want you to tell me, in that dome, where is the state? Is it on the left hand side, or whether it is in between, or whether it is on the right hand side? Now, the most important part here is the temperature is 80 degrees. Do you agree with me? For 80 degrees temperature, saturation pressure is a 47.41. What that means is, if you want water to evaporate, your pressure has to be 47.41. Is this pressure greater or lower than 2 bar? So just to give you an idea, this is 47,410 Pascal, and the current pressure, which is 2 bar, is 2 into 10 to the power 5 Pascal. So 2, 1, 2, 3, 4, 5. So tell me, can you see that the saturation pressure is less than the actual pressure on the liquid, which means it is going to be in liquid state. So based on this combination, it's going to be liquid, not liquid plus vapor, not saturated vapor, just liquid. And when this is liquid, the density, the specific volume can come from directly 0.0102. Density is given as 1 divided by specific volume. Then the enthalpy of liquid, pure liquid, is m Cp delta T, where Cp is the specific heat, mass is given as 2, Cp of water is 4.18, the temperature is 80 degrees. So 80 minus 0, because 0 degrees is considered as reference. And the entropy, this is the equation that we discussed this in last class, is M Cp ln of T divided by T reference. MCP ln T divided by T reference. M is 2, Cp is 4.18, ln, and here T needs to be in Kelvin. 80 plus 273, 273. So this is how you solve the very first problem. And the answers are, so this is meter cube per kg. If you want capital V, this will be 2 multiplied by 0.0102 meter cube. This is kilojoules. And this is going to be the entropy. Everyone clear about this problem? Okay. Next problem. Problem 3.4. And I want one of you to help me out with this problem, because this problem expects you to read from the steam tables. So determine mean specific heat for superheated steam at 1 bar between the temperatures T is equal to 150 and degrees C, and T is equal to 200 degrees C. Now the question is, how do we find out this mean superheated mean specific heat? Now mean specific heat is also called as the average specific heat. So first and foremost, what I want you to do is, I want you to tell me what is enthalpy of the steam when temperature is 150 degrees C. What is enthalpy of the steam when the temperature is 200 degrees C? And before we even go there, I want you to go back to this normal distribution sort of curve and tell me, where are we? Look at pressure, so temperature is say 150. I want you to look at table A4, pressure 150. Can you see that the saturation pressure is 475? So what needs to happen is, you can see this pressure is at 1 bar. So there is another table that you can refer, which is table A5. So table A5. 1 bar P is equal to 1 into 10 square, which is 100 kilopascals. So I want you to locate 100 kilopascals. 100 kilopascals is 1 bar. 1 bar is atmospheric pressure. Do you agree with me? 1 bar is atmospheric pressure. So if the temperature is 150, what does it mean? It means the steam is boiling. The water has boiled. Okay, now check this out. If you are looking at the pressure of 1 bar, do you agree with me that this temperature is going to be 100 degrees C? Do you agree with me? Because at 1 bar, the water boils at 100 degrees C. The temperature is 150, which means all the water has boiled, got converted into steam, and now the steam is superheated. Everyone understood this? So the steam is superheated at 150 degrees, and the steam is also superheated at 200 degrees C. Do you agree with me? Now, how do I find out the enthalpy of steam? How do I find out enthalpy of steam? When steam, yeah, question? What? Pardon me? Yeah. So now I need you to find out which table would you refer. The table that you should be referring is table A6. Because if you look at table A6, I want to show you a shortcut. Look at table A6. Can you see at table A6, you have superheated vapor. Can you see the pressures are given? Pressures of 0.1 megapascal. What is 0.1 megapascal? 0.1 megapascal is 0.001 into 10 to the power 6, which means it is 0.1 bar. Are you with me? Table A6. Now I need to table A6. Table A6. Table A6. Yeah, table A6. Now on table A6, this is the specific table for the superheated water. And Alex, I want you to read this figure. Can you see that it shows the value of pressure? And in the parentheses, it shows the saturation temperature. Are you with me so far? So if the pressure is 0.01 megapascal, mega means 10 to the power 6. Bar means 10 to the power 5. So 0.01 megapascal means 0.1 bar. Are you with me? So water will boil at 45.8 when the pressure is 0.1 bar. Everyone understood this? Now I want you to go through this table and find out the location when the pressure is 1 bar and the temperature is 150. Go to the table and find when the pressure is 0.2, so which is nothing but 0.2 bar, 0.3 bar, 0.5 bar, 0.6 bar, 0.7 bar, and then this is 1 point, yeah, 1 megapascal, 0.1 megapascal. So which is, I want you to go to yeah, 0.8, 0.9. You have 0.9. 0.1 megapascal. So 0.01, 0.05 and 0.1 megapascal. This is one bar. 0.1 megapascal. Understood? The third table on the right, the very first on the top. Are you able to look at 0.1 megapascal table? Everyone, that table corresponds to 1 bar. Now go to the table and tell me what is the enthalpy when the temperature is 150. 2776 kilojoules per kg. And tell me what is the enthalpy when the temperature is 200 degrees C. 2875 kilojoules per kg. Do you agree with me? Now, before you go further, were you able to find those numbers? Before you go further, I want you to look at the solution that I gave you. Can you notice in solution they have used an equation to find out the enthalpy? But you don't have to do that. You can directly read those from the steam tables. Everyone understood this? Everyone understood this? Any questions? Now, next thing, before we go any further, here is something else I want to show you. So now I want you to go to the chart. I have given you two charts. One is the Molière diagram, where what you have is you have enthalpy and entropy. So you have two plots. You have a TS diagram for the water, which is figure A9. You have figure A9, wherein what you have is you have pressures and temperatures. You can use either figure A9 or figure A10. Let's look at figure A9. That figure A9 has tons of information plotted on top of each other. You have understood this? There are lots of lines. On y-axis, what you have is you have temperature. On x-axis, you have entropy. Now, right now, what information we have? We have the information about temperature. Do you agree with me? Temperature is 150 degrees. So track that temperature horizontally and tell me where does that intersect? Where does that intersect with 1 bar line? Where does it intersect with 1 bar line? And once you identify that point, the enthalpy value will be written right next to it. Now take some practice, but I want you to do this exercise. First, track where the temperature 150 degrees C is. Look at that horizontal line and see where it intersects with 1 bar of pressure. Are you able to track it? You may need a magnifying glass, but you should be able to track it. I can quickly show you. So 150 degrees, go horizontal, 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 and then you will notice these lines. These are the bars. You see 10, and then you get all the way over here 1. You see that? And then if you draw the horizontal line, that is where you see the enthalpy scale. And you would be able to get the exact same answer as you got on the table. Yeah. Correct. First slide in reading the maps. Okay. Now you have the enthalpy of petrol. Now here you see the carbon. Now 8, 6, 4, 3, 2, 1, 1, 1, 0. And then once you intersect over here, can you see that there is this enthalpy state from this state go down. Understood how to read it now?
Yes.
So you see that? This is the point of intersection. Draw a line. You see that this same as the enthalpy box on the table. Same thing for 200. 200, 200, 200, 200, 200. This intersects over here. You see that? And now what we do is
I'm trying to stay on.
yeah.
I started
You understood? Go down, track the intersection one. Yeah, good. Right, good. Yeah. Now what you do is working week. This is just the game.
So this just gives the ballpark.
At the end of the day, the value will be small. Everyone understood? Yeah. Story does not end here. Now I want you to turn the page. Go to the next slide. Now on that diagram, Fourier diagram. Look at the Fourier diagram and with your sharp eyes, tell me what is the enthalpy value. Turn the page, correct? Your pages are not separate. You turn the page. Leave no page unturned. Fourier diagram. Right. Found the Fourier diagram? Oh. That's why I gave you a big graph. Okay. Now, can you read the Fourier diagram? So, if you look at the Fourier diagram, it's the diagram. Fourier diagram, what you have is on the y-axis you have enthalpy, and on x-axis you have entropy. Now, just like last diagram, can you find out the pressure lines? Can you see 30,000 bar, 25,000 bar, 20,000 bar, 15,000 bar, all the way to get a line of 1 bar. So you track the line for 1 bar and then see where it intersects the temperature 150. where it intersects 150, and then draw a horizontal line, and that would give you the enthalpy.
Oh, I think so 150 degrees.
Yeah. It's like 300. Lowest it goes.
Oh, you don't have complete Muller. Are you sure you don't? Oh yeah, 300.
Oh yeah. Sorry, you don't have the complete Muller diagram, but when I was a student, I had a Muller diagram like this huge size, and then the same information what we got from the charts, the tables, you can also get from Muller diagram. So Muller diagram can also give you the same information. But the beauty of Muller diagram, the table says, the chart is, you get all the information in one shot. So basically, once you locate where that point is on that diagram, it gives you specific volume, it gives you enthalpy, it gives you entropy, and all the information that you need.
Everyone understood?
So that is the important thing. We can okay. Now the next problem is problem 3.5. Now, okay, let me finish this problem. So now you have this enthalpy at the end, you have the enthalpy at the beginning. If you want to find out the Cp, what you have is delta H is equal to M Cp delta T. Mass is 2 kilogram. Cp we have to find out. The temperature is 200 minus 150. And here you are going to get 2875 minus 2776. And that should give you the value of Cp. Are you with me so far? Any questions? Next problem. Oh, there is no mass. So my bad. Then this is 1. M is 1. M is 1. So you can get C. So next problem, problem 3.5. So yeah. Yeah, so basically Cp is given as specific heat. Specific heat unit is kilojoules per kg degrees Celsius. So what is the definition of specific heat? Is the amount of heat to be added to 1 kilogram of mass to raise temperature by 1 degrees. If you look at the unit of delta H, can you see this delta H unit is kilojoules per kg. So on the right hand side, this has to be 1. So because it's an average specific heat. Next problem is P3.5. So identify the type of steam in the following three cases using the steam tables and necessary calculations. So I want you to tell me the answers. I want you to tell me the answers. First part, mass is equal to 2 kg, pressure is equal to 8 bar, enthalpy 5538, and temperature is equal to 170 degrees C. The easiest way to identify the state of the steam is using the steam tables or the Morier chart. So quickly look at, tell me what is the state. So for the first case, now what you want to do is you need to know the enthalpy is 5538, pressure is 8 bar, temperature is 170 degrees C. So tell me, what is the state of the steam? So what we do is we go to the table, find the table corresponding to 8 bar. And what is the temperature? I don't have my steam table. So what is the temperature corresponding to pressure 8 bar? What is Tsat? (170°C). 170 degrees C approximately. Then what is the value of HF and what is the value of Hg? What is the value of HF? 7. Yeah, and Hg? 2767.9. Now Hg is given in kilojoules per kg. Now what I want you to do is I want you to observe one thing. In the problem, the pressure given is 8 bar. Pressure given is 8 bar. Temperature is 170. Can you see for pressure is equal to 8 bar, temperature is 170 degrees C, which means this indicates that it is on this line. So you have to kind of go in 2 steps. So it indicates temperature, it is over here. Temperature is 170 and the pressure is 8 bar. Now the enthalpy is given as 5538. So we need to find out the specific enthalpy, H per kilogram, which is 5538 divided by 2. So what is the value 5538 divided by 2? 369 kilojoules per kg. Now in steam tables, approximate values are okay. Can you see that this value is close to the value that is given to us? Which means I can say that this is this point. So it's dry. Why is it dry? Because dryness fraction x is equal to 1. Please note x is equal to 0 here. X is equal to 1 here. And the enthalpy is 2767. So dry, saturated, steam. Are you with me so far? Why is it dry, saturated? Because enthalpy of the steam per kilogram is same as the enthalpy of dry saturated steam, Hg, from the steam tables. That's why it's dry saturated steam. Everyone understood this? Understood? Good. Now the next problem. Next part is 1 kilogram of steam. 1 kilogram of steam at 2250 kilopascals. 2250 kilopascals. But it is interesting, it is saying occupying the volume. So capital V is given as 2742 meter cube. And M is equal to 2 kilogram. So 1 kilogram of steam. Or is it 1 kilogram? Oh, 1 kilogram of steam. Okay. Now the pressure is given 2250 kilopascals. And volume is given. Now the question is, how do we find out the state of the steam? So there are two ways to solve this problem. The easiest way to do it is, I want you to look at the Molière diagram or the PS diagram and find out, locate 2250 kilopascals, which is 22.5 bars. Find out a point 22.5 bar and 2742 meter cube volume per kg. Are you able to track a point which is 22.5 bars and 2742
It's supposed to be 0.2742.
oh, 0.2742. Yeah, you're right. Ooh, yeah, 0.2742. So find out 0.2742. Huh? Well, if your eyes are trained, you can use any table as long as you know where to look for. Yeah, tell me.
Saturated water.
Is it saturated water or right? So that doesn't make sense. So please note for pressure 22.5 bar, specific volume, which is Vg, is given as 0.078. Do you agree with me? Meter cube plus kg. But this specific volume is much greater than the specific volume at Vg. That means this is a superheated vapor. 2000, oh yeah, 2550, correct, sorry, 2550. I will can I borrow your, let me show you easiest way to do this. Let's go by the Molière diagram. So we are at 25 bars. So you go to 25 bars, it goes to 30 bar, and then what you notice is you will look at they have given not the specific volume, but they have given intensity. So you can have to invert it. Let me see the PS diagram. PS diagram is also given in terms of density. So you have to find. So what you need to do is to locate this point on the Molière diagram. You have to find out the density. Density is 1 divided by 0.078. And then find out the point which is 25.5 bar and this density. And you would notice that would be in the superheated region. What is this density? 1 divided by 0.078. No, V is, no, 0.27, sorry. V is 0.27. Rho, so density is 1 divided by 0.27 kilogram per meter cube. So tell me what is 1 divided by 0.27? $3.7. Now I can see 3.7 kilo. So it is in between, and then if you track it down all the way to the constant pressure line, which is 25.5, you can see that it becomes, that point is somewhere over here. 3.10. 3.7, then drag it down all the way to the pressure 3.5, and then So it is in the superheated region. Were you able to locate that point on the Mobius diagram? If you don't have a Mobius diagram, the easiest way to do it is to catch the specific volume. Specific volume is greater than Vg. That means that is superheated. So the state is superheated steam. Okay, so now this becomes superheated steam. Now the next last part of this problem is C, 1 kilogram of steam at 60 bar with enthalpy 2470.7 kilojoules per kg. So now we are at 60 bar and enthalpy is 2470. So what I want you to do is, first I want you to go to the table, pressure is equal to 60 bar. Tell me what is the value of Hg and Hf. For pressure is equal to 60 bar. Tell me what is the value of Hf and Hg. And tell me the temperature also, saturation temperature. At 60 bar, what is the saturation temperature? Huh? What is it? 158 degrees Celsius. What is the value of HF? 678. Hg 670. 670. And Hg 3000. Okay, now I want you to notice this value of H is in between HF and Hg. Are you with me so far? So this value is in between HF and HG. This is HG. This is HF. This is 1213.8, 2708.4. So which means you are somewhere over here. Are you with me so far? So 2470 is equal to 1213.8 plus the quality factor or the dryness fraction solve this equation and tell me the value of X. So this is a wet steam. 0.8. Yeah. Compressive? Compressed liquid, you mean? Compressed liquid is saturated liquid. So liquid, or just say liquid, it in theory cannot be compressed. So you just say saturated liquid or just liquid. So this is the region of saturated liquid or compressed liquid. This is the region for gas. This is the region where you have liquid plus gas. Okay. With that, we have covered important types of problems. Now, there are quite a few problems that I have given to you, but it's not a spectator sport. So what you need to do is you need to work out these problems and get yourself familiar with how to solve these problems. Everyone understood this? Okay. Now, next part is I want to work out some problems from chapter 4. These are the problems from chapter 3. And we have to work out the problems from chapter 4. If you remember what chapter 4 is, chapter 4 is first law applied to closed systems. Okay. And please take out the notes for chapter 5. Chapter 4, sorry, please take out the notes for chapter 4. And we will work out problem number 1. Problem number 1. These are the notes. Does everyone have the notes? A certain gas occupies a volume of 0.3 meter cube at pressure 2 bars. Pressure is equal to 2 bar. Volume, this is the total volume. Zero 0.3 meter cube. Temperature of the gas T is equal to 350 Kelvin. The gas undergoes a thermodynamic constant volume process until the pressure raises to 7 bar. So the V is equal to constant. So if you look at the PV diagram, what you have is initially the pressure is 2 bar, volume is 0.3. And what's going to happen is it's going to be a constant volume process, and temperature here T is equal to 350 degrees Kelvin. And there is going to be a constant volume that goes all the way to 7 bar. So this is a constant volume process. Determine the temperature at the end of the process. So P2 is equal to 7 bar. So we have to find out the temperature at the end of the process, change in the internal energy, which is delta U, change in the enthalpy, which is delta H, and change in the entropy, which is delta S. So we need to find out change in the enthalpy, change in the entropy, and change in the internal energy. Quick question. What is the work done in constant volume process? Correct. So work done in constant volume process is 0. But even though the work done is 0, the gas law P1 V1 is equal to R T1, P2 V2 is equal to R T2 is going to be same. So what it means is I can use the equation P1 V1 divided by T1 is equal to P2 V2 divided by T2. Pressure, initial pressure is 2 bar. Now, since it's a constant volume process, I can take V1 is equal to V2. So it cancels out. The T1 is given as 350 Kelvin is equal to P2 is 7 bar divided by T2. So solve this and tell me the value of T2 in Kelvin. So that is going to be 1225. 1225 Kelvin. Change in the internal energy, delta U, is always given as M CV delta T. This is the equation that we derived and we referred. So where M stands for mass, CV, the value for air, you should remember 0.712, or you can use the tables, multiplied by delta T, which is 1225 minus 350. And that gives you kilojoule per kg. So it's air. For air, R value is 0.287 kilojoules per kg Kelvin. CV value is 0.712 kilojoules per kg Kelvin. CP value is 1 kilojoules per kg Kelvin. So these are the values Cp and Cv values for the air. This you can get from the table or you can remember. Delta H is M Cp delta T. M is 1, Cp is 1, delta T is 1225 minus 350. That gives you 5. And then how much, I don't know, you can find the mass or you can write the answer in kilojoules per kg. If you want to find the mass, you can use the equation P1 V1 is equal to M R T1. P1 is 2 bars. V1 is 0.3 is equal to M times 287 times 350. So that will give you the value of mass. The last part is entropy. And since it's a constant volume process, entropy change is given as M Cv ln T2 by T1. Cv is 0.712. Ln T2 is 1225 divided by 350 kilojoules per kg. So let me explain this problem one more time. In this problem, what we have is we have a constant volume process. In constant volume process, as the word suggests, the volume is going to be constant, which means the work done in constant volume process is going to be 0. If I were to show this process onto a PV diagram that is shown on the right hand side, initial pressure is 2 bar, initial volume is 0.3 bar, final pressure is 7 bar, final pressure is again 0.3 bar. So to solve this problem, first is asking us to find out the temperature at the end. So we have to use the state equation or the gas law. P1 V1 divided by T1 is equal to P2 V2 divided by T2. And when you substitute these values, you are gonna get this temperature T2, which is 1225 Kelvin. Now, once you have the final temperature, he's asking us to find out change in the internal energy, change in the enthalpy. Change in the internal energy is always given as M times specific heat at constant volume, which is Cv, multiplied by delta T. Change in the enthalpy is given as M times Cp multiplied by delta T. And change in the entropy is given by the equation mCv ln T2 divided by T1. Everyone understood this? So we have discussed these equations in last class. So if you look at the slides and charts, we actually derived some of these equations. Okay, now I'm going to solve next problem. Problem 4.2. A rigid tank of 0.2 meter cube. Now understand this tank is rigid, which means that tank is not changing shape. So this tank is 0.2 meter cube. It contains the nitrogen at pressure P is equal to 350 kilopascals and temperature T is equal to 15 degrees C. Now the tank is exposed to a constant temperature source. So tank is exposed to a constant temperature source. So 273 plus 15 gives me 288 Kelvin. So T1 is 288, T2 is 170 plus 273 is equal to 443 Kelvin. Which results into 50 kilojoules of heat. So Q is equal to 50 kilojoules is transferred. So 50 kilojoules transferred. So one, find final state of gas. Change in the internal energy. Change in entropy. Now, the gamma value, which is the ratio of Cp divided by Cv for nitrogen, is given as 1.4. And value of Cv is given as 743 joules per kg Kelvin. So in this problem, first and foremost, I want you to tell me what type of process is this? Understand, it's a rigid cylinder. I mean, it's a rigid container. So the rigid container means it's not expanding, not contracting, which means the volume of the container is going to remain constant. So this is a constant volume process. In this constant volume process, you have an external temperature source which is at higher temperature than the initial temperature, so that the heat is flowing in. So the heat is going in, and that heat is 50 kilojoules of heat that is going in. And now what we want to do is we want to use this information to find out the final state of the gas. So to find the final state of the gas, we need to know that what is the temperature, what is the pressure, what is the volume. So for that, we can use the equation P1 V1 divided by T1 is equal to P2 V2 divided by T2. Initial pressure is 350 kilopascal. Initial volume is 0.2. Initial temperature is 288. P2 is something that we have to find out. The final volume is same as initial volume. The temperature is 443. Solve this equation and then you'll be able to get the value of pressure kPa. Change in the enthalpy, change in the internal energy, delta U is equal to CV times delta T. CV for the gas is 743 multiplied by delta T is 443 minus 288 kilojoules per kg. Change in the entropy, delta S is equal to CV ln T2 by T1. So which is nothing but 743 ln 443 divided by 288. Now the important part is if you want to find out the total values, you can do that. So for that we will use P1 V1 is equal to M R T1. This V is the total volume. So 350 kilopascals. V1 is 0.2. M, the R value for the gas we don't know, but we know Cp divided by Cv is equal to 1.4. Cp minus Cv is equal to R. Cp is 1.4. Cv minus Cv is equal to R. So R is equal to 0.4 Cv. So Cv is 0.4 times 743 times the temperature is 288. So with that, you will be able to find out the value of mass, and you can find out this mass by the specific enthalpy, specific internal energy and specific entropy, and you'd be able to find out the total entropy and total change in the energy. Everyone understood this problem? I'll explain this problem once again. So in last class, we looked at different types of processes. We looked at constant pressure process. We looked at constant volume process. We looked at constant temperature process. We also looked at isentropic process, and we looked at polytropic process. For each of these processes, we found out what was the work done. For each of these processes, we found out what was the change in the enthalpy, what was the change in the entropy, what was the change in the internal energy. Let me quickly write down this. This is the equation that I wrote in last class. And these are the two most important equations that you should remember. For any process, change in the internal energy is CV multiplied by the change in the temperature. For any process, change in the enthalpy is CP multiplied by the change in the temperature. Everyone understood this? Entropy equation is CV ln T2 divided by T1. So these are the only four equations that you need to remember to solve any problem. We also looked at the derivation of R, which is R is the gas constant. So we looked at the equation of H, which is the enthalpy, is given as internal energy plus flow work. Flow work from the gas law, PV is equal to RT, because M is considered to be 1, because V is the specific volume. So it's the volume per unit mass. This in this equation, and you get this fundamental equation. The difference between the specific heats is nothing but the value of the gas constant. Are you with me? And that equation. So right now, if you look at the two problems that we have solved, it was a constant volume process, and we applied these equations, the constant volume process. Everyone understood this? Now what I'm going to do is, we are going to apply the same equations for the constant pressure process, which means throughout the process, pressure remains constant. Then we will apply the same equations for the constant temperature process, and we would apply the same equations for polytropic and isentropic process. Everyone understood this? The process is going to remain the same. The approach is always going to remain the same. Just you need to pay attention to what type of process is it. With constant volume, constant pressure, constant temperature, isentropic or isothermal, or isentropic or polytropic. Okay. Next problem. Problem 4.4. Any questions on these problems? Okay. Now, so if you look at this, this is kilojoules per kg. Now, I can actually, I want to follow the exact, so if you want to find this is the specific internal energy. So if I multiply this by mass, then I get the total internal energy. If I multiply this by mass, then I get the total entropy. So it's totally up to you if you want to find out the specific quantity or if you want to find out the total quantity. So mass, you can calculate mass here, right? Yeah. So it's totally up to you how you want to find out. Any more questions? Okay. Next problem. Example 4.4. Okay. In an experimental determination of specific heat of air at constant pressure. So what we want to find out is specific heat of air. 50 grams of air at constant pressure was heated. So mass is equal to 50 gram. Was heated from T1 is equal to 14 degrees C. So we need to express this in Kelvin. From 14 degrees C to 74 degrees C, T2. For a period of T seconds. So time is equal to 300 seconds. So it was like this. The power consumed is 10.04 watts. So gamma value for air is 1.4. So we have to find out the value of Cp. We have to find out the gas constant, and we have to find out the density of air at temperature is equal to 0 degrees C and pressure is equal to 0.1 megapascal. So these are the different equations. So first and foremost, we have to find out how much of heat was supplied. Power is equal to Q divided by delta T. So power is 10.04 Q divided by 300. So 3000 joules. So power, the heat Q is equal to 3000 joules. And this 3000 joules Q is nothing but M times Cp times delta T, where M is the mass, which is 50 divided by 1000. Cp value we have to find out, and change in the temperature is 74 minus 14 is 60, and from this you should be able to find out value of Cp. Gamma value is Cp divided by Cv. Gamma is given as 1.4. You can find out the Cp value from here, which is 1.004 kilojoules per kg Kelvin. 1.4 is equal to 1.004 divided by Cv. So from here, you should be able to get the value of Cv. And R is equal to Cp minus Cv, which is 287 joules per kg Kelvin. Now the last part, they are asking us for the density. To find density, P1 V1 is equal to R T1. So pressure is 100 kilopascals. V1 is to be found out. Value of R is 287. Temperature is 0 degrees C, which is 273. From here, you'll get the value of V1. Density is equal to 1 divided by V1. So I'll explain this problem real quick. Now, in this problem, what you have is you have the mass of air as 50 kilogram. This 50 kilogram of air is heated by a resistance heating. And after you heat, what happens is the initial temperature was 14 degrees. After heating, the temperature becomes 74 degrees. This is actually a calorimeter experiment that can be used to find out the specific heats of the substances. Now, what you do is you measure the amount of power that is supplied to the resistance heater. And the way you measure the power is basically you take the voltage, you multiply that by the current, and then you measure the amount of time that resistance heater was turned on. So the resistance heater had some voltage, some current. Voltage times current gives you the power, and that resistance heater was turned on for 300 seconds. Within 300 seconds, the temperature went from 14 to 74. And based on this, we have to find out all the specific heats of the air, where the gamma, which is the ratio of the specific heats for the air, is given as 1.4. So first, you have to find out the heat that is supplied, power times power multiplied by the time in seconds. Heat is equal to mass times specific MCP delta T. So with that, we are able to find out the value of Cp. Once we find out the value of Cp, then what we do is we use this equation, which is gamma is equal to Cp divided by Cv, and then we can find out the value of the gas constant, which is R. The next question he's asking is for the given values of temperature, for the given values of pressure, what is the value of the density? So for that, we have to use the equation P1 small v1 is equal to R T1. T1 is given, T1 is given, R we found out. So we can find out the specific volume. 1 over the specific volume is nothing but the density. Everyone understood this? Any questions? Okay. So next problem. Problem 4.5. One kilogram of nitrogen at a temperature 150 degrees C occupies a volume of 0.2 meter cube. So mass is equal to 1 kg. Temperature is 150 degrees C. Volume is 0.2 meter cube. The gas undergoes a fully restricted constant pressure expansion without friction. The final volume, so V1 is this, T1 is this, V2 is 0.36. So if I were to show this process onto a PV diagram, you had a constant pressure expansion. So this was 0.3. This is 0.36. And the process went something like this. So 0.1 to 0.2. So you start with 0.1, you go to 0.2. Calculate the final temperature. So we have to find out T2. Find the work done, which is W. Find the heat transfer Q, and then change in the entropy. So this, for that, we have to use the equation P1 V1 divided by T1 is equal to P2 V2 divided by T2. Now it's a constant pressure process, which means P1 and P2 are going to be the same. So V1 is 0.3, T1 is 273 plus 150, V2 is 0.36 divided by T2. So solve this and you'll get the value of T2. So that gives you the temperature at the end of the process. So let me see. Now what we need to do is we need to find out the work done. Work done is nothing but in the case of constant pressure process, you have P times V2 minus V1, because work done is equal to integral P dV from 1 to 2. P is constant, that comes out. So you have dV 1 to 2. So you get P V2 minus V1. So pressure value, did they give us the pressure value, temperature? Yeah, pressure value can be found out. So pressure value can be found out using the equation P1 V1 by T1 is equal to M R. V1 P1 V1 is 0.2. Temperature is 273 plus 150 is equal to value of mass is 1 kilogram, and the R value for nitrogen is 297. So with that, we should be able to find out value of P1. So once we know value of P1, which is the same value as P2, substitute this value here. V2 is 0.36 minus 0.3, and then you'll be able to find out the work done in joules. Are you with me so far? The next part is we have to find out the heat transferred. First law of thermodynamics for the closed systems is given as Q is equal to delta U plus work done, or PV. So you can use this equation to find out the value of so delta U plus W. Delta U is M CV delta T plus value of W we know from here. Mass is 1, value of CV is 743 multiplied by the temperature, which is, you will get the value of T2 from here. Can someone tell me the value? I don't think I gave you the solution to this problem, but find the value of T2. So 700.4 Kelvin. What is the work done here? Find the pressure. Tell me what is the pressure? This is pascals, right? Newton per meter. Then substitute this value here, and then you will get the work done. $37.68. And here, last but not least, is 761 minus 273 plus 150. Plus 37.68. And the last is entropy, which is Cp ln T2 by T1. So Cp value can be found out since R value is given. Cp minus Cv is equal to R. Cp minus 743 is equal to 297. So you can get the value of Cp. Substitute that value here. 761. And that should be able to give you the value of entropy. Okay. Any questions? I would solve one more problem. Problem 4.6. A mass of 0.8 kilogram of air at P is equal to 1 bar and T is equal to 25 degrees C is contained in a gas-tight, frictionless piston cylinder device. So what we have this piston cylinder. This is gas-tight, frictionless. The air, so initially the air was pressure P1 as 1 bar, P2 as 5 bar. And during that process, the heat is transferred from the air so that the temperature inside the air, inside the cylinder remains constant. Now, I want you to read this sentence very, very carefully and tell me what type of process is this? constant temperature. So T is equal to constant. Now when you have T is equal to constant, which means look at this, P1 V1 divided by T1 is equal to P2 V2 by T2. Since T1 is equal to T2, this goes away and the equation is given as P1 V1 is equal to constant. So this is the constant temperature process. Now we have to find out the work done during the constant heat transfer. So we have to find out Q and we have to find out the work done. Now, before we actually write this, please remember, wherever you go, if it's a closed system, the first law of thermodynamics is applicable. Q is equal to W plus delta U. W is nothing but integral PdV. Delta U is nothing but CV multiplied by delta T. Since it's a constant temperature process, delta T is going to be 0. So which means in the constant temperature process, Q is equal to whatever is the work done. Work done in the constant temperature process, remember we derived this, is nothing but P1 V1 ln. Do you remember P1 V1 ln V2 by V1? V2 by V1 or P1 V1 ln P2 by P1. So since in this case pressures are given 1 into 10 to the power 5 multiplied by V1, volume is V1 is not given, but have they given us the value of it's air, so we know the value of so we can use the equation P1 V1 is equal to M R T1. P1 is 1 10 to the power 5. V1 mass is given as 0.8 multiplied by R is 287 multiplied by T1 is 273 plus 25, and from here get the value of V1, substitute the value of P1 V1, value of V1 which comes from here, ln P2 is 5 divided by 1, and that gives you the work done. And for the constant temperature process, Q is equal to work done. Is it compression or is it expansion? Oh, it's compression. So this is P1 divided by P2. So this is 1 divided by 5. Okay, and I'm not going to solve these problems, but I just want you to, I will give you hints to solve these problems. So Next problem that I want you to look at is from example 4.7. In example 4.7, you have two processes which are combined. So first, what you have is you have an isobaric process, pressure is equal to constant, followed by an isothermal process. So example 4.7. So in this example, you have an isobaric process followed by isothermal process. So total work done is nothing but the work done during the isobaric process, which is the rectangle, and then the work done during isothermal process. So the shaded area is the total work done. You can apply the first law of thermodynamics for individual processes from process 1 to 2 and 2 to 3 and find out the work and heat interaction. Everyone understood this? The problems that we have solved so far, we looked at the constant volume, constant pressure, and constant temperature process separately. But we can combine those three together, but we need to solve each segment separately, and that should be able to give you the answer. That is the next problem. Everyone understood this? Please work out that problem after going home. Because your next class you will have a quiz. That quiz will be based on the problems that we discussed for chapter 3 and the problems that we discussed for chapter 4. So chapter 3 and chapter 4 problems that I worked out in today's class will be on the last quiz, which is on Thursday. The next problem is again, you can actually do mix and match. So problem 4.9, what you have is you have a PV to the gamma process, and again you have to find out the work done, the heat interaction, final process temperature, and so on. 4.11, you have an isobaric process followed by an adiabatic process. So basically the same processes, you combine them together and find out the properties. Everyone understood these? So please go to the handout, and if you have any questions, welcome to ask me those questions in next class. Now I will give you about 5 minutes, maybe 3:07. 5 minutes break, and then we will start the last lesson of this. So in this chapter, we are going to talk about what do we mean by control volumes. We will apply the first law of thermodynamics to the control volumes, and at the end of the day, we would apply the energy balance equations at the beginning and at the end. So control volume means you have an open system. Remember, the difference between the open and the closed system is mass remains constant. Mass does not go in and out of system when the system is a closed system. When the system is an open system, the mass is allowed to cross the boundary, the heat can cross the boundary, and work can cross the boundary. So in this chapter, we are going to talk about the conservation of mass principle. We will talk about two types of systems. One is a steady flow system. Other one is an unsteady flow system. You have to apply the first law of thermodynamics as the conservation of energy principle. And again, at the end, you have to derive the equation, sum of energy remains constant no matter where you are. There are different types of systems, steady flow systems. There are nozzles, there are compressors, there are turbines, there are throttling valves, then there are mixers, heat exchangers. So we will be applying the first law of thermodynamics to these different types of systems. And the last part of this chapter is a very small part wherein you have to apply the energy balance equation to the general unsteady flow processes, where the process is not steady, and basically there is something called as uniform and non-uniform flow. We will talk about it when we get to that part. So first and foremost, conservation of mass principal states. Mass cannot be created, mass cannot be destroyed, it remains constant. Unless you use nuclear energy, where you destroy the mass and all of a sudden you get huge amount of energy. Closed system in which the mass does not cross the system boundary. Mass remains within the system boundary. Control volume is where mass can cross the boundary, and you need to take into account how much of mass that is coming in and how much of mass is going out. And again, this is a very simple example. Say if you have hydrogen, if you have oxygen, and if they react with each other, you get H2O. But please understand, the mass is going to remain constant. Now, conservation of mass is as given by this integral equation, rho dVAC, where V is the velocity, A is the area, rho is the density. When you perform this integration, you are going to get something called as a mass flow rate. And typically, if you look at the flow through pipe, if you look at the boundary, the flow attached to the boundary or the circumference of pipe, internal circumference of the pipe, it is fixed. So the flow velocity here is 0, flow velocity here is 0, and in between these two, the flow varies parabolically. If you were to integrate that velocity and then divide that by the area, you can actually get the average velocity, which is basically gives you what is the velocity if you were to look at the average of all those arrows and divide by the number of arrows. A classic example is the bathtub, wherein what you have is you have some water that is coming in, you have some water that is going out, and the difference between the inflow and the outflow is nothing but the mass that is inside the bathtub. Now, please understand, wherever you have the control volume analysis, as you can observe here, mass coming in is 50 kilograms, mass going out is 30 kilograms. So 20 kilograms of mass is staying inside this control volume. Imagine if this were to be a closed container, you have to always assume that the total capacity of mass does not exceed the capacity of the containment. In other words, you can't let that control volume to explode. So that is one important assumption that when you have to take into account when you try to solve the problem. Now, conservation of mass, if you want to write this as an integral equation, if you write this expression down as an integral equation, you will take an arbitrary volume, and then what you are going to do is you are going to look at the boundary, and then you are going to find out the total mass within control volume, and you will find out the mass that is coming in across the boundary and the mass that is going out across the boundary. In other words, the general conservation of mass principle states that rate of change of mass inside the control volume plus rate of change of mass going across the control surfaces, the total sum is equal to 0. And what this simply means is, check this out. This shows you the velocity. This is called as the normal direction, which means that is perpendicular to the surface area. So the component of velocity, which is along perpendicular to the surface area, multiplied by the area dA, multiplied by the density, that gives you the total mass that is crossing the control surface. Please understand, whenever you are looking at the control surface and you are looking at the mass interaction, to find out the mass that is crossing the control surface, you need to find out the velocity which is perpendicular to the control surface. To find the velocity perpendicular to the control surface, you need to multiply, you need to find out the dot product, or you have to find out the projection of the velocity with respect to the unit normal, and then multiply that by the density and the area. If you expand this equation further, convert this equation into a momentum equation, then what you get is you get the classic Navier-Stokes equation. Now, this same equation can be rewritten in a slightly different form, which again, this is nothing but, if you look at the bathtub example, the mass which is accumulated in the control volume is the difference of the mass coming in and the mass going out. Which means if you have intake or inflow of 3 gallons per second, if your outflow is 1 gallon per second, which means the tub would be filled with 2 gallons per second. That's what this equation implies. Incoming 3 gallons per second, outgoing 1 gallon per second, which means the control volume is filled. Control volume is filled with 2 gallons per second. That is what this equation implies. Moving on, why this concept of normal is very important, because please understand, fluid can, whenever you think about the fluid does not flow perpendicular to area. Fluid particles can flow in very many different directions. But to find out the flow, you need to find out the velocity which is perpendicular to the area. So that's why you need to take the projection, and the way we take the projection is taking the dot product with a unit normal. Now, the mass balance for the steady flow process is, now please understand, in this problem, we are not allowing any mass accumulation, which means whatever mass that is coming in, the same amount of mass is going out. So in this case, there are 2 inlets. Mass coming in is 2 kilograms per second. Mass coming in is 3 kilograms per second. If you do not want mass to accumulate inside this control volume, the mass going out has to be 5 kilograms per second. And believe it or not, these principles are universal. For example, if you look at the Kirchhoff's law in electrical circuits, if you take EGR340, then the electrical systems class, you use something called as the Kirchhoff's law. Kirchhoff's law also says the same thing. The current leaving the joint is equal to the current that is coming in and current that is going out. So at joint, you can't hold any current. The only way to hold current or energy is add an accumulator. Now, another example is, now I want to tell you think about something called as the compressible flow. and incompressible flow. Now, imagine if you have liquid, liquid is assumed to be incompressible, which means the density does not change. On the other hand, if you look at the gas, it's considered to be compressible because the density is dependent on pressure. And when you have a compressible system, the compressible systems, the compressible air or gas or steam, they behave differently at different speeds. Now, how many of you have seen those fighter planes that they go at Mach 1, Mach 2, Mach 3? Have you seen that they show something called as the sonic boom when the plane goes out? Now, what is Mach? Mach is the velocity of sound through that medium. So now what happens is, as soon as air reaches the velocity of Mach 1, as air crosses the sound barrier, the properties of air, they change. I'll give you a very simple example. Think about, imagine you are watering your plants. Okay, you are watering your plants and you have this water hose. And what you do is you try to close the opening of the hose. What happens? You see there is increase in the velocity. If you try to reduce the area of opening, you notice that the flow goes farther. So you increase the velocity. Have you seen this? In other words, if you have a converging nozzle, the velocity increases. Do you agree with me? If you have a converging nozzle, velocity increases. Everyone agrees? Now I want you to imagine the space shuttle. Have you noticed that at the bottom of the space shuttle, they have nozzles, but they are diverging? Why? So let me tell you the reason for that. The space shuttle, when the gases are coming out, they are coming out at the speed higher than the speed of sound. You have a converging nozzle that can increase the velocity when the velocity is below the sound barrier. What happens once you cross the sound barrier? Just to give you a crude example, that gas is becoming like a solid, like a sluggish solid. So when you have the solid coming out through a converging nozzle, it does not increase the velocity. In fact, it decreases the velocity because one particle affects or sort of impedes the motion of the other particle. That's why when you are at the supersonic speeds, the nozzles are diverging. So when you are at subsonic speeds, nozzles are converging. So if you look at these fighter planes that they go to sonic, they're out. Basically, those converging nozzles become sort of diverging nozzles, and the plane changes shape because the control surfaces that allow you to control at subsonic speeds cannot control when you achieve the supersonic speeds. So at subsonic, things are different. At supersonic, things are different. So at subsonic speeds, you have converging nozzles. At supersonic speeds, you have diverging nozzles. And why the nozzles are diverging? Because the flow which is coming at supersonic is sort of this, since the speed is so high that all these particles are sort of compressed against each other, and it's like, if you want to visualize, it's like a sluggish behavior. So the normal rules of engagement are off. So that's why there is that completely different types of aerodynamics that you should study. at supersonic speeds. Now, again, in the working, if you have a fluid that is in between these two boundaries, the most important part is when you have a fluid flow. For the fluid to flow, you need to do some work, and that work is called as the flow work. Work that is needed to induce the flow, and that is called as flow work. And definition of flow work is force is equal to pressure times area, and what you do is basically pressure times area multiplied by the distance that is traveled, L, that gives you volume. So the flow work is given as P times V. Now, it's again very important. I give you a very simple example. If you have a fluid flow, if you put maybe a block of wood in the flow, you will notice that wooden block moves, which means there is some work done, and that work done is nothing but the flow work that is needed for the flow to enter the control volume and to exit the control volume. So it is very important for the flow work. And what you are going to see here is nothing new. You have seen these equations before. These equations are nothing but you have the total energy, which is the internal energy U, kinetic energy mv square by 2, and the potential energy mgc. So we also talked about this as the concept of head, where head is nothing but energy per Newton. Same equation is written over here. U is an internal energy, Ke is the kinetic energy, and Pe is the potential energy. Now, if you add the flow energy, you get this total energy, which is flow energy plus internal energy plus kinetic energy plus potential energy. And this total energy equation, and what I can do is I can actually add PV plus U. I add PV plus U, and I get the equation for H. So I get H is equal to U PV. So this equation can also be written down as H, which is the enthalpy plus V plus kinetic energy plus potential energy. Now I want you to understand what is the difference between the liquid flow and the gas flow. Whenever we are looking at the liquid flow, we assume the temperature of liquid at intake and exhaust is the same. So typically we ignore the enthalpy. And instead we consider the value of pressure energy. But when we are looking at the gaseous medium, we observe that temperature could be different at the intake and the exhaust, and that gives you this equation for H, which is enthalpy, kinetic energy, and potential energy. Now, again, in the same equation, so if you have a non-flowing fluid, which means there is no flow work, then your equation is going to be internal energy, kinetic energy, and potential energy. If you have a flowing liquid, then you need to take into account the effect of flow energy, which is P times V, and then U, which is internal energy, kinetic energy, and potential energy. Now, please try to understand once again, what does that mean? It means if you have a reservoir, that reservoir there is no movement of liquid or there is no movement of gas inside the reservoir, that is considered as non-flowing fluid. Fluid means it could be liquid or it could be gas. Flowing fluid means what you have is you have this gas that is flowing, then you need to take into account the flow energy, internal energy, kinetic energy, and potential energy. Now, the next thing what you want to think about is how much of energy is contained in a unit mass. So if you look at the energy that is calculated per unit mass, multiply that by the total mass, that gives you the total amount of energy that is transported. Instead of multiplying by mass, if you multiply that by mass flow rate, what you get is you get power. And again, we solved some of these problems. So if you want to find the power, you multiply the total energy per mass by mass flow rate. If you want to find out just the total energy, you need to multiply that by the mass. Now, in steady flow process, the basic assumption is whatever is coming in, that is going out. The only difference here is in steady flow conditions, the mass and the energy content of control volume remains constant. Now, if you start to study unsteady flow processes, that's a whole different area of research and study in thermodynamics. Because when you look at the unsteady flow, you have lots and lots of variables that you need to take into account. But one simple example of unsteady flow is this assumption that the fluid properties at inlet and exit, they remain constant. They could be different somewhere in between, but at inlet and exit, fluid properties remain constant. You can also relax this assumption and derive the expression, but that is out of the scope of thermodynamics. Now, if I want to, at the end, please try to understand what we have here is, we have this energy in is equal to energy out. So on the left hand side, what you have is, you have the heat energy, work energy, and all other initial energies, kinetic energy, potential energy, internal energy at point 1 is equal to the heat that is going out, work that is going out, and all the energies such as kinetic energies, potential energies at the exit. So if you want to work out the problems, what you need to do is you need to look at the intake, inlet, and the outlet, and find out the heat interaction, work interaction, heat interaction, work interaction, and the total energies. A word of caution. Even though I have shown like Q in, W in, Q out, W out, the sign convention still holds. If the work is done on the system, either at inlet or at outlet, that work is going to be negative. The work is done by the system, either at inlet or at exit, that work is going to be positive. If the heat is going in at the inlet or at the outlet, that energy that Q is going to be positive. If the heat is coming out at the inlet or at the exit, that heat will be negative. Yeah.
What would we do if the heat or work was not coming in either?
So basically, what we do is whenever we look at the steady flow processes, inlet, which means for steady flow processes, you have to identify the boundary. You have to find where the heat and energy interactions are coming in and going out. Now, the coming in and going out is with respect to mass, which means when I say in, this is all the interaction related to mass going in. Out means all the energy interaction related to the mass going out. So in means if whatever is this energy interaction when the mass is coming in. This energy interaction when the mass is going out. For example, if you have a spherical control volume. In spherical control volume, imagine that you have mass coming in, coming in from 3 different directions and mass going out from 2 different directions. When I'm going to write down the energy at in and energy at out, I would sum the energies at those 3 inlets and I would sum the energies at those 2 outlets. That is how I would analyze this control volume. Does everyone understand this? Yeah. So next thing is again, how do we do the energy analysis of the steady flow system? Now, same example, what you have is you have the water in, the mass coming in, mass going out, and you have some heat coming in, some heat going out, and at the end, what you do is you set up the equation which is called as the energy balance equation, which means what you do is you look at all the energy interactions corresponding to when the mass is coming in. You look at all the energy interaction corresponding to the mass going out. If there is no loss, then you know that all the energy can neither be created nor be destroyed. Whatever energy that is coming in has to go out. And then what we do is we apply the energy balance equation and find out. Now, what I'm going to tell you here is this gives you a very general form of energy balance equation. But I don't want you to remember this energy balance equation just like this. We will look at the different types of systems and then we will write down the energy balance. We'll find out if the work and energy interactions are positive or negative and solve the problem. So for an example, this is the energy at exit. This is the energy at intake. The difference between these two energies is nothing but the difference between the heat and work interaction. This is what it means. Now, I just want to give you a little bit more explanation. Please try to understand the first law of thermodynamics that we wrote. The first law of thermodynamics is given as Q. The first law of thermodynamics, never ever forget this. Q is equal to W plus delta U. Q is the heat, W is the work. This is change in the internal energy. First law of thermodynamics for steady flow systems is something like Q is equal to W plus delta E. And that's what is shown over here. Delta E means E2 minus E1. E2 is the energy at exit, E1 in the energy at inlet. So first law of thermodynamics for a closed system is given as Q is equal to W plus delta U. First law of thermodynamics for an open system is given as Q is equal to W plus delta E. Delta E stands for the total energy at exit minus total energy at inlet. And that is what that equation talks about. Now, if you look at the energy analysis for steady flow system, you can have a steady flow system, which means you can have a pipe and you have a fluid flow. There could be a resistance heater, there could be a fan, and there would be some shaft work done by the fan. The resistance heater would heat the fluid, and so on. And again, you have to be consistent in terms of units. And please understand, even as you increase the velocity, the kinetic energy changes. So a small change in the kinetic energy is it significantly affects the work and energy transfer. So whenever you are trying to solve the problems, what you need to do is you need to take into account all the different types of energy. Now, let me give you some examples of the steady flow devices that you probably have seen. So heat exchanger is a steady flow device. Turbine is a steady flow device. Pump is a steady flow device. Now, this is a very simple example wherein this is a gas turbine, and the gas turbine is a steady flow device. Now, please try to understand what you have is, again, this is a General Electric turbine. What you have is, you have a compressor, you have a combustion chamber, and you have a turbine or the expander. Cold air comes from the compressor. Compressor compresses the cold air. Then what it happens here is the fuel is burned in the combustion chamber, and all the hot gases, high temperature, high pressure, are expanded in the turbine. So if you look at the jet engines, they have these types of turbines. Another example is called as the nozzle and diffuser. Now please try to understand. Nozzles are used to increase the velocity. Diffusers are used to decrease the velocity when the velocities are less than the critical speed of air or sound. So as long as we are looking at below 1 Mach, then the nozzle is used to increase the velocity at exit. Diffuser is used to reduce the velocity at exit, and the energy equation is, or energy balance, is given on the right hand side. Same thing, if you look at the diffuser, you write down the equation for the energy balance, and if you have an adiabatic diffuser, which means there is no heat transfer, if there is no work done, it means all the change in the enthalpy is because of the change in the speed or change in the velocity. So the flow accelerates inside the nozzle because the exit velocity is much greater than the intake velocity. So this is a very simple example. But initially inlet pressure is 250 psi. Inlet velocity maybe is don't know if they gave us the inlet velocity. So inlet velocity is very small, but what's going to happen is at exit, all that change in the enthalpy would get converted into velocity, and the flow is going to come out at an extremely high speed, and that's what increases the velocity. Another classic example is you have turbines and you have compressors. So basically, turbine is used to generate is an electric generator. It's using steam for steam generation, gas turbine, or even turbine is used in hydroelectric plants. Compressors are used to compress or to increase the pressure. There are actually I want you to understand the difference between compressor, fan, and pump. Compressor is used for gases to increase the pressure. Fan is used for gases to increase the flow. So compressor increases the pressure energy, fan increases the flow energy. Now please try to understand. You don't use compressors as fans because compressors are designed to increase the pressure, not velocity. Fans are used to increase the velocity, not pressure. And pumps are used to pump liquid. You do not use pumps in gas. Gases cannot be pumped. What you do is you basically use a compressor to create the flow of gases. Now, if you look at the equation for the compressor, then you will notice that you have the shaft work being done here. You have inlet, you have exhaust, and then what you do is you do the energy balance at inlet and exhaust. Look at the energy and the heat energy and the work energy and write down the energy balance. Again, for steam turbines, in steam turbines, we have high pressure, high temperature steam that is expanded to get the work out. In compressor, you do the work. In turbine, you get the work. So that is the difference between compressor and turbine. We talked about throttling again and again. Throttling is nothing but expansion through a very narrow opening. In throttling, enthalpy remains the same. Pressure drops down, temperature drops down. So basically, enthalpy before throttling is equal to enthalpy after throttling, but the pressure drops down and temperature drops down. In air conditioning and refrigeration system, throttling is an important concept. And we will study this. Next thing is mixing chamber. Think about your hot and cold water faucet. You have hot water coming on one side, cold water coming on the other side. And what you get is you get the mixture. So heat that is imparted by the hot water, heat absorbed by the cold water. At the end of the day, you get the balance out. So basically, heat rejected by the hot water is equal to the heat gained by the cold water. And you write that energy balance equation and you get this equation for mixing. Same thing with the heat exchanger. There are three types of heat exchangers. One is a parallel flow heat exchanger where both the flows go in the same direction. You have a counter flow heat direction wherein both the flows go in opposite direction, and a cross flow heat exchanger where both flows they go across each other. So for an example, the radiator in your car is a cross flow heat exchanger. And here are the equations for the heat exchangers. That what we are going to do is we will study these in next class and I would derive those equations. And again, whenever you have heat exchangers, you have to look into the heat rejected by the cold fluid, heat rejected by the hot fluid is equal to the heat absorbed by the cold fluid. That gives you the total flow. Again, pipe and duct flow is an example of steady flow processes, and you can apply the first law of thermodynamics. Again, electric heating of house. In this example, what you have is you have the heat that is imparted by the resistance heater. You have some heat that is rejected, and then depending upon the walls are adiabatic or not, or insulating or not, you can actually find out the energy balance. The last part, which I want to briefly touch upon, is energy analysis of unsteady flow processes. It's not an easy problem to solve. You have to look at something called as the uniform flow process assumption, which assumes that the fluid flow at inlet or exit does not change properties with respect to time. And in that case, what you have is you have a control volume. You actually look at the mass balance and the energy balance across control volume. And at the end, you write these equations down as mass coming in minus mass going out is the change in the mass. And then what you do is you write the energy balance taking into account the mass multiplied by energy going out. mass multiplied by the energy coming in and the total change in the energy. So unsteady flow processes are typically more complex. And for example, I don't know if you have looked at the charging process of your air conditioning and refrigeration system. If you were to charge air conditioning system, that process is nothing but an unsteady flow process. Basically, if you were to open an expansion valve or a valve and let the steam come in or go out, that is also going to be an unsteady flow process. Now, in this chapter, we briefly looked at the theory of conservation of mass. We looked at the flow work. We looked at the energy analysis. We looked at the steady flow systems, and we looked at unsteady flow systems. In next class, we are going to take each and every type of system. For example, nozzle, diffuser, turbine, pump, heat exchanger, and we will work out the problems specific to those systems. We will derive these energy balance equations again, because please try to understand that theory will not make sense unless we actually work out the problems. So we'll look at those different systems, we derive the energy balance equations, and then we will solve those energy balance equations. So next class is going to be our last class. In last class, what I'm going to do is I'm going to derive derive the energy balance equations for these 5 to 6 systems. We'll work out the problems, and then we will, in next class, we will finish the last chapter, which is on the second law of thermodynamics, and that would conclude our EGR340. Next class, you are going to have a quiz, and that would be the last in-class quiz. Today's quiz, I couldn't finish the material in time, so I gave you as a take-home quiz, but it would be included as part of your in-class quiz grading. But a request, please follow the honor code. Treat this quiz as if you are taking this in class, and it would be open notes but closed books. So with that, I'm going to stop here today, and I would be happy to answer any more questions